very happy to start our day with Moni, who will talk about communication complexity, streaming, and computational assumptions.
Thank you. So I'll be talking about various works I did with my students. You can see them here. And the first one I'll talk about is the Shahar. I think that's the only picture I found of him. So the ones at the bottom are not my students. This is the Tel Aviv Museum. Okay.
This is a high-level overview.
Okay, so what I'm going to talk about is what effect do crypto assumptions have on algorithms in relatively simple settings. So basically what we're going to do is choose a setting where randomness helps. We can't do much if it does not help to begin with. Show a good algorithm against an inactive static adversary. Then show what an adaptive adversary can do and discuss whether crypto can help. And if it can help, show that the tools that we're using are essential. And this is, of course, the relationship to this workshop, where we'll try to figure out the minimal assumptions. And then, of course, we'll repeat the whole thing with a different formula. So let me say right at the beginning, so that because I probably prepared way too much material, I'm not going to get to the end of it. Let me just state the general approach I'm asking is, can we automate the process? Is there like a way of figuring out without doing all the hard work that we're going to do in this talk? Is there any way of doing it? Are there any simple criteria we can use and to determine whether crypto helps and what exactly are the tools? Okay, so there have been lots of examples in the past. I mean, I picked a few here. Maybe the most related one are adversarially robust property preserving hash functions of Boyle, Lavinia, and Vaikunantan. But definitely I can think of many other things here and elsewhere. Okay, what will we see? Of course, I thought of talking about two directions. One is related to communication complexity. This is work with Shahar Cohen, mostly appearing in Crypto 2022. And the relationship there, the question there is, what is the connection between low communication complexity protocols, collision-resistant hash functions, and secret key agreement protocols? And then we'll talk about streaming and specifically card guessing. And this would be joint work with Boaz Menuhin and relationship to what's called mirror games with Ro'i Magen. And I'll end up mentioning low memory permutation generation. Okay, so let's talk about communication complexity, which I assume we all know and love. We have two players, Alice and Bob. They're not strangers to this audience, Alice and Bob. Alice has an input X, Bob has an input Y. They talk, exchange messages, and they wish to compute a function of their inputs, and they exchange messages, and then they want to compute the value of the function. So somehow from their communication, they should figure out what is the value of the function. And the goal is to exchange as few bits as possible. Okay, to characterize given a function, how many bits do we need in order to compute it? And so obviously the complexity of a protocol is a number of bits in the worst case, and the complexity of a function is the complexity of the best protocol. And we'll concentrate on equality. I will just mention that there could be other predicates. So the function we'll be discussing is equality. Alice has X, Bob has Y. They want to decide whether X equals Y. Most of the stuff we'll be saying is relevant to any non-trivial predicate which does not have redundant rows or columns. And furthermore, we just you need it to be separable predicate that is given x1 and x2, you can find a y which separates. But really think just of equality. That's and there's still some issues. I mean, I haven't finished telling you exactly what I mean by a protocol. There is the issue of how exactly are the messages? Are we allowed, do we care about the number of rounds, or are we trying to limit very much the number of rounds? And we'll be concentrating on in this talk, we'll be concentrating on the simultaneous message model, where both of them send the message simultaneously to a referee who then computes it. So they never directly interact with each other. But some of the stuff I'll be saying is relevant to the interactive model as well. So the deterministic complexity is often in, and not always, are obviously counter. For instance, for equality, if you insist on deterministic protocol, you need to send n bits. The other issue is the use of randomness. There is the shared model where the two parties share a random string, which is chosen independently of their inputs. So that's the big distinction. That's what we're going to concentrate in this talk, is exactly what is the relationship between randomness and the inputs. So usually in the shared public randomness model, there is a shared random string, which is chosen independently of the inputs. And then there is the private randomness model, where the parties do not, all they have is their own shared randomness.
Either way, it's independent input, it's just random.
Pardon?
It's independent input by definition, because it's uniformly distributed.
Well, but perhaps if it's in the sky, just in crypto, we know that you can, there is always a question whether the inputs are chosen based on the CRS.
Oh, okay, so are we in a setting where the parties are honest? Or?
I'll say exactly who the parties are, because I'm going to introduce, and this is perhaps a character that usually doesn't appear in communication complexity, the adversary.
Okay.
The adversary sees the randomness and chooses the inputs accordingly. This is what we'll be trying to protect ourselves against such behavior. One quick question. Also a slow one is okay.
So do we have any properties about the biases of each bit? Because if you're trying to...
Oh, we're assuming, we're not going to talk about such things. We'll assume a very good randomness.
1 by pi is okay.
Truly random, that's not the issue. The issue is whether somehow, as part of the excitement of running the protocols, somehow the randomness affected the inputs, which can happen. We know that it can happen inadvertently also. Let's say it affected the time it took a previous protocol somehow to share randomness. Therefore, it affects the inputs. Therefore, you cannot argue independence. So obviously, the shared public randomness is stronger if it's truly independent. It's stronger than the private randomness. And these issues are more or less, these two issues are more or less orthogonal to each other. Now, what we know about equality in the interactive model, we know that with shared randomness, to get constant probability of error, you need just to exchange just one bit. Yeah. Two-sided error. Yeah, so for equality, I mean, yeah, we can talk about whether we're talking about two-sided error, one-sided error, Las Vegas style, everything. Obviously, there are analogs of every complexity class you can imagine. There are analogs here. We'll be thinking of perhaps two-sided error, but with equality, you really don't have to worry about the two-sided. It's just one side. And if you have shared randomness, then all you need to do is exchange one bit, because, for instance, you can take the inner product with, think of the shared randomness as being defining a vector over GF2, and you take the inner product, X and Y, take Allison's to Bob the inner product of the shared randomness with X. Bob sees whether it's consistent within his input and announces the result. And it even works. I haven't quite said what is the simultaneous message model. It also works in the simultaneous message model. Okay, on the other hand, in the interactive model, if you don't have private randomness, then you need log n communication. And this is always true. That's the largest difference you can have from a result of Neumann. You can simulate in the interactive model, not in the simultaneous message model. You can always simulate the shared randomness. Okay. And another observation is that there are no function in the interactive model. You cannot go beneath the log n for any non-trivial function. Okay, so what is the simultaneous message model?
Wait, what does it mean? Say the last sentence again. What do you mean? There are things you can do deterministically. What do you mean you can't go below? Oh, log n is not the randomness, it's the round.
Not the round, the number of bits.
Communication. Sorry, I thought it's the randomness. Got it.
Okay, the simultaneous message model. You have Alice and Bob, each looking at their own inputs and sending one to the referee, sending a message to the referee from some message space, MA and MB. The referee gets the two messages and decides what the result is. Okay, so you can think of it as some sort of sketching. Each one sends a sketch, and then you can tell the result. And the referee can tell the result. That's I think, the big motivation behind this model, though it's already in the original Yao paper on communication complexity. You already defined this model. And we want a probability of error that the correct result will be computed with probability of error of at most epsilon to answer your question. Okay, so here is for equality testing. Okay, so with shared randomness, we already more or less saw the right protocol. What you can do if you do have shared randomness, you just need to send a single bit. But let's see, you can do something non-trivial even if you don't have any shared random. In the private bits model, you can do something. What can you do? Alice, each one of them encodes their input using a good error correcting code. They put it inside a square root by C, square root by C, square, yeah, the matrix. And Alice sends a random row, Bob sends a random column, Alice sends a random row. They intersect in one location. The referee completely ignores the other stuff and concentrates on the intersection and sees whether it's equal or not. And in a random code, if it's a good code, then a random location is going to be different with roughly probability proportional to the alphabet size. So, this gives us something. This gives us a communication protocol of square root of n. This is the square root of n communication protocol. And in general, this is this is the best possible. Neumann and Segedi showed that the size of the two messages there is at least the sum of the sizes at least square root of n. Babai and Kimmel, and in general, will be using their approach. The product of the two messages is n. So you get, of course, that at least one of them is square root of n. And in general, you can get here, instead of n, you can get here the deterministic complexity. You can make the protocol deterministic with this much.
This is only for equality, yes?
This is for equality, yeah. But I'm saying the Babai Kimmel result is sufficiently general that you get a deterministic protocol out of it. Okay.
Do the protocol need to Very small.
Pardon?
Do the protocol need to repeat to make sure the average is very small?
To repeat? Yeah, I mean, it depends on now it's up to you. I mean, there is no issue of parallel repetition here. Parallel repetition simply reduces the probability of error.
And those lower bounds are also for.
This is for a fixed
error.
probability. For you want 1/3 probability of error, you get this result. Okay. So, so the question is, can we reduce the communication complexity by assuming certain hardness assumptions, and what assumption do we need? And exactly how I already hinted, we need to define the model more accurately. Okay, so what are the issues? Exactly when is the randomness chosen, as we were discussing? Who maintains state? If the randomness is chosen at a certain point, do you need to also maintain state from step to step or something like that? And the exact power in terms of computation of an adversary. And we'll see actually two models, the preset randomness model and both of them are made up names. I mean, it's not, we made them up for this work, a preset randomness and the free talk stateful model. And we'll see tight bounds on communication complexity assumptions in model, well, almost tight bounds, and when you close one eye. So, okay, so in the preset randomness model, the preset randomness model is more or less when there is shared randomness in the sky in the cirrus model, but somehow the inputs were chosen based perhaps on this shared randomness. Somehow it leaked because affected, who knows why. So in this model, we'll see that breaking the square root of n lower bound for equality implies the existence of distributional collision resistant hash functions. We'll see it in a constructive manner. And assuming as I said, I'm going to talk mostly about the simultaneous message model. I mean, it definitely simplifies our life because you know exactly there is one message from each party and that's it. But we also have the same type of results regarding interactive communication. But there we instead of square root of n, of course, we have log n. If you go below log n for communication complexity, for interactive communication, then you are using distribution and collision resistant hash functions. There are no protocols of constant communication, whatever assumption you need. And as I mentioned, we'll be using their proof, their lower bound proof well, actually, we'll be using it even for the interactive case, even though their proof is for the non-interactive case. And those of you who are smart, which I assume is everyone here, you probably figured out that if you have collision resistant hash functions, then you can use it in order to improve the communication.
Those who are smart or those who can read?
I guess I'm not so smart. How do you break the log n?
Okay. I meant for the simultaneous message model, but even for but you can break the log n even for the interactive one. Okay, you have something to think about.
We're not that smart, you know.
Okay. Okay. So this is for the preset randomness, for the what we call the stateful free talk model. What we assume is that Alice and Bob talk to each other. Now we are, let's say, outside the model of sketching. Before it was exactly like sketching. Now think of it, Alice and Bob talk to each other, maintain a state. Before the inputs are chosen, they talk. They maintain a secret state. Each one has their own state. And the communication complexity is measured only after the pre-processing phase. But also the inputs are chosen after the pre-processing phase. So the adversary sits in the middle, listens to their conversation, and then selects the inputs. And what we'll see is that very efficient protocols against a rushing adversary, of course, I'll have to define everything here, imply the existence of secret key agreement protocols. Okay. And by very efficient, I mean that for a C-bit protocol, you have probability of error, which is, let's say, 2 to the minus 0.7C, something like that. So for each bit, you're getting something, essentially, almost something. So if you have such a protocol, then we know how to convert it into a secret key exchange, secret key agreement protocol. Yeah.
So does the adversary get to see both the secret states or just the key?
No. They don't see the secret state. Otherwise, there is no advantage. He may as well choose. It may be part of the public randomness. So no, the secret state is secret for a reason. It's called secret state because it's not part of the power of the adversary.
So let me ask a question kind of more generally. You want to say that you cannot make the protocols more efficient without essentially relying on assumptions. And then kind of the idea is if you do rely on assumptions, you can do it easily. And
in both cases, if in this case, if you assume that you have a secret key agreement protocol, then you have a C-bit protocol with probability 2 to the minus C.
Okay, because then you'll share a thing and
yeah, so and it's good against a rushing adversary.
okay, good.
How does the free talk compare to correlated randomness?
To correlate, that's a good question. But the issue here is that everything you can do with correlated randomness, if you have secret key agreement, you can do, if you have, so at least if you have oblivious transfer, you can do it here. The other way, because the other way is not entirely clear.
In correlated randomness, the adversary sees the randomness, right?
Yeah. So
in the other direction, it's because of the amplification issue of the 0.7. It's really the limits of amplification.
Let's take it offline, just not to confuse with the yes and no. So just a reminder about assumptions in crypto. So we have a bunch of things that are equivalent, one-way function, minicrypt, a whole bunch of applications that are equivalent to private key encryption and whatever. That's minicrypt. We have a collision-resistant hash function. And we have secret key agreement. It's not, secret key agreement definitely implies one-way functions. CRH, we think that it's close to it, but not quite. It's not. And we have oracle separation of all these assumptions. And it's worth mentioning, so collision-resistant hash functions means that it's hard to find any collision. And in order to separate one-way hash functions from CRH, you could consider a collision finder. Given a collision finder, one-way functions do exist, but CRHs, of course, do not exist. And the random oracle is an example of separating a secret key agreement from CRHs. Because random oracle, we do have the CRH. Right. So as we mentioned, collision-resistant hash functions, we want a family that are of hash functions. We want them to be efficiently computable. Given h, a description of little h, and given x, it's easy to compute h of x. It's hard to find collision for every polynomial time adversary in large enough security parameter, where a random a little h in the family. Given h, it's hard to come up with x different from x prime that collide. Should be negligible in the security parameter lambda. And as I mentioned, you can separate them that's originally from Simon, Dan Simon in 98, and using a random collision finder. And the other observation is that if once you can compress by a little, you can compress by a whole lot. So if you can chop one bit, you can chop many, many bits. Okay, distributional collision resistant hash function. It's a family of hash functions where it's hard to come up with a random collision. They were defined by Dubrov and Yishai, and the blank box separation still holds. From blank box separation from one-way function still holds, and the interesting thing is that with such a DCRH, you can still do some interesting things that we don't know how to do with, let's say, just constant round statistically hiding commitment schemes. Okay, so these are we're starting with a preset randomness. So
don't Ilan and Elon have a paper showing how to go from DCRH to CRH? Some minor caveats? Or
with caveats, yeah. With caveats. I mean, right. That's why okay, the question regarding this work is whether you can whether you can do directly CRH. We don't know how to use their stuff to do directly CRH without the caveats that they have. Okay. Sorry?
So using distributional version, you can get constant round statistically hiding commitments, but not two round.
I think not. No.
We don't know or impossible.
Oh, it means oracle separation?
Don't know.
I think with the simplest thing, it would probably be the okay. So how do we get succinct protocols from CRH? Well, in the preset randomness model, let's say it's a simultaneous message model. If you have a function going from n bits to lambda bits, then you have a protocol with complexity square root of lambda instead of square root of n. And in the preset public coins interactive model, you can get log lambda. And what do? Well, the public string is defines a hash function h, and you replace x with h of x and continue as before. That's it. So instead of having an n bit input, you have a lambda bit input. So we're breaking the square root of n lower bound in this model. Okay. Now we want to go to lower bound. So we want to somehow start with the protocol and define a hash function for it. Okay, so we have.
When you use the CRH, you also need to change like nature to be efficient, right? Or...
Yeah. As I said, here's the protocol is nature chooses the. We're now assuming so our actors are Alice and Bob, of course, the referee. Let's think of the referees being deterministic. We have Alice and Bob. They have to be also now because we're adding the computational assumptions. They themselves have to be efficient. We have the randomness is chosen, the CRS or whatever that is chosen, and then based on that, here this is how it works. Based the randomness is chosen. The adversary sees the randomness and chooses x and y. And if we are assuming that the adversary is efficient, so after seeing the random string RP, the public string, x and y are chosen. Okay. So This is nature.
And this is the only thing the adversary does.
Yes. In this protocol, there are no. I mean, actually, we'll see in the rushing model they can see, choose inputs gradually and things like that. See what Alice is sending and then decide what Bob's input is. But here, let's keep it simple here. Nature sees the common random string, chooses the inputs X and Y. And then they send their inputs. The message, not their inputs, of course. They send it to the referee who has to determine whether X equals Y. Okay. And now let's so RP is going to be the common randomness. Then put space capital X and capital Y for Alice and Bob. Alice gets little x, Bob gets little y. MA and MB are message spaces, whatever Alice and Bob can send to each other. It sends to the referee. They're sending little a from little ma from capital MA and little MB from capital MB. And they also have private randomness, of course, that is not known to the adversary to begin with. Otherwise, we'll be in the deterministic setting. Or not exactly the deterministic, sorry, we wouldn't be in the deterministic setting, no, actually, but they do also have their own shared private randomness. And so Alice sends, as I said, Alice says MA, Bob sends MB, and the referee decides on the result. And Alice's distribution is given X, given RA, her private random tape. So that determines her message, and same thing regarding Bob. Okay, so this is what a protocol looks like. Okay. So what we'll be using, yeah.
So how do you measure error? So what's the error? What's the notion of error actually?
Pardon?
What's the notion of error in this context?
Oh, whether what the referee outputs is the correct result, whether if it says 1, they're equal, if it says 0, they're not equal.
For every pair of messages, or
Pardon?
for every pair of messages?
For every pair, yeah. No, not for every pair. No. Okay. So the notion of error is that did the adversary force a wrong result on Bob? The adversary knows the protocol. Adversary knows the protocol, knows the shared randomness. If you can find an X and a Y and make the referee output a wrong result, then the adversary succeeds. Okay, we want the probability that the adversary succeeds to be bounded by epsilon. It's not. It doesn't make sense at this point to talk about for any X and any Y. Right.
So if the adversary was unbounded, it
Then
would
it would
collapse to
make
the
sense.
previous normal definition.
Exactly.
Does there exist such an input?
Exactly. But then we know that you cannot go. That's a good point. Without computational assumption, we're back to the model where let's say Baba and Kim prove the lower bound of square root. Yeah.
The order of quantifier and protocol matter. So what
Yes, of course it does. But here, so again, you see the adversary sees the common randomness, chooses X and Y.
Yes. I mean, what if it's become like much more trivial if I design like a protocol for every adversary.
No. Here, okay, the adversary, you said, so again, you decide on the protocol, you design the protocol, RP is chosen, the adversary chooses X and Y.
Yeah, so here, like, we have like a secure protocol against like every adversary.
Yeah.
Like,
yes, exactly.
So what happens if, like, say there's like a particular distribution over XY that's of interest, and we just need like for every like.
We know, I mean, it's not clear that it's equivalent, but we know that it's very hard to take advantage of it. How can you say that you don't have a universal collision finder? We don't know how to take advantage of the fact that we know, but we know with, as usual, we don't know exactly how, we don't know exactly anything about how the inputs are chosen. So it's not very reasonable to design a protocol assuming you know the adversary, because you don't know, you don't have enough information about exactly how X and Y were chosen. So it's hard to model it.
But is it computational problem, like say?
How do you, I mean, you are in a setting, you are not sure exactly how your protocol is going to be used. So.
Yes, that makes sense. Okay.
I mean, in a sense, I think what Jan is trying to say is like, if we think of the PRG analogy, if you could use kind of a Nissan Wigderson style PRG instead of a CRH, use a Nissan Wigderson style CRH instead, and maybe that you can actually do.
You use because you know because you will be fooling, it will be fooling the particular answer.
Exactly.
No, but I don't think it makes sense in this case. Because you don't know exactly the process of how the inputs were chosen.
Like in de-randomization, you can have.
In de-randomization, it's true.
But like there they
Yeah, no. In de-randomization, of course, it's true. But here, there's a protocol, like I'm thinking of sketching or something like that. I don't see how it would make sense to assume that you know how the inputs are chosen. Okay, so as I mentioned, okay, so we'll be using characterizing multiset. For every X, for every input X, there exists a multiset of possible messages characterizing its behavior on X. Instead of running Alice to begin with, we can approximate the protocol by a uniform sample from this multiset. So this is not very surprising because I could, by definition, I think there exists a huge, I mean, all possible messages are such a set. But the point is that you have not a very, you don't need a very large, multiset. And that's the point. And such a multiset can be found by sampling, by running the protocol relatively few times. You can find such a multiset. And the property that we want from this multiset, from this subdistribution, so to speak, is that for every possible message that Bob will send, so we don't know what Bob, we don't care about Bob's input, we care about Bob's message. For every possible message that Bob will send, the behavior on a true Alice and the behavior on choosing Alice from TX should be roughly the same. The probability that the referee outputs 1 should be roughly the same in both cases. So so that's the important thing, is that we're doing it for every possible message that Bob sends, not for every possible input that Bob sends. This allows us to sort of, at the end, we'll do some sort of union bound. This will allow us to do a union bound over all possible messages rather than all possible inputs, and therefore we'll get the result that we want. And so, as I mentioned, you can simply.
Sorry, can you go back one side? When you say the expected value, you mean over a random element in T sub X?
For every possible message that Bob sends.
What is Q? So Q, you choose a random message in T sub X?
Yes. Okay. So the way we'll construct it is we'll simply sample T times, where T is something like log the message sizes of Alice, of Bob, sorry, we'll sample from it T times. And this is going to be a good characterizing multiset with a constant probability.
Simulating message that fools Bob. Fools the referee with all possible standard.
No, again, it's I'm not trying. We're not trying. What we want to say that I don't care. Once I fix TX, I don't care what message Bob what message Bob sends. I want the property that we'll have is that the referee's behavior is going to be the same on both this distribution and on a true protocol.
So I think if I can, Rachel, she's saying, think about all what the referee does with any one of the possible messages from Bob is a distinguisher. And this is kind of a generator with a small space that is fooling all of these distinguishers.
With a small, not space, small C.
Yeah, small C.
Exactly. No, you. I think that you get 2 points for that. Okay. Okay. So this is essentially how. What we're going to do. The way we'll construct the hash function is it's going to be defined by the public random string, which is going to be fixed, and by T random tapes for Alice. And for any x, the value of the function is the multiset, simply the multiset, the behavior of Alice with all those random tapes, with all those little t random tapes. And as you can see, what is the size of the output? It's going to be t times the size of these messages. The size of these messages is the size of is MA, the size of the messages that Alice sends. So the total size is going to be the size of the messages of Bob, so the size of the messages of Alice times the size of the messages of Bob, which if you break n, then it's going to be less than n, so you certainly get some compression once you have a non-trivial protocol here. And so we have the function h is compressing, and if you have an x and x prime which share a characterizing multiset, they induce a bad input for the protocol because you can pick them. You can pick x and x prime, and then choose y that separates them, one of them in the case of equality. And then the sum of the failure on one or either on xy or on x prime y, the sum of the failure probabilities is, let's say, at least 0.8. So at least one of them is going to be. Okay, so we can use. So the whole point is that we can take this and use it as a collision. We can use a collision breaking the h as a DCRH to one breaking pi as a computational one, as a computational equality protocol. And we will use the collision finder in order to find bad inputs for the protocol. So we go from breaking the protocol, we go from breaking the hash function to breaking the protocol, and therefore we have a construction. If we have a good protocol, we conclude that we have a good construction for DCRHs. And why, at this point, of course, the question is, I mean, everything I said sounds like a CRH, not a DCRH. But no, the point is not all of them are going to be characterizing. We can't quite cover everything. So we're not going to be characterizing for everyone. We're characterizing for most of them. So therefore, we need the DCRH. And the interesting question is, can we bypass this? Okay, so this is regarding the preset model. I see that I've really been too ambitious. I'm probably not going to go beyond the next topic, the one on preset on a free talk. So what do we mean by stateful free talk? So Alice and Bob exchange messages freely. We don't count it. But all this happens before the inputs are chosen. If it happens after the inputs are chosen, of course, they will decide on the send X and Y to each one. They maintain a secret state. The adversary eavesdrops and then selects the inputs. And communication is measured only after the pre-processing phase. Okay, now I mentioned rushing adversary. What do we mean? So the inputs are chosen by computationally bounded adversary, depending on the public discussion. But in the rushing adversary, the referees first sees what message Alice is sending and only then decide what is the input to Bob. There's more power to the and so we give more power, not to the referee, to the adversary. We give more power to the adversary. So this is one thing we allow. Then we also have a patient adversary where the adversary sees, starts a session and decides whether this is going to be the one where it corrupts or not. Sees, decides whether it's the one it corrupts or not. And do it several times until it decides now, sees Alice's message, then says, this is the one I'm going to corrupt. So these are
messages, multiple sessions with different inputs each time?
Yes.
And the adversary chooses the inputs adaptively all the time.
Again, I don't know. So this is a weakness of, you could say, a weakness of our lower bound, because we're going to use both of these things. I don't think you really need them. This is the way we will convert an adversary to one breaking the secret. The way we'll convert a protocol into one that is a secret key agreement will be needing these two properties. Okay, secret key agreement, which we all again love. We have two parties. They exchange messages. They have no prior common information. At the end, they agree on a secret key. The key should be secret, so no eavesdropping adversary, assuming a passive adversary, can compute the key with non-negligible advantage. Actually, we want it to be distinguishing from random. We know that we can go from one to the other. And of course, public key encryption implies the secret key agreement. So once we have secret key agreement, things are really nice. You can you have a good protocol with the stateful preset public randomness with very little communication, and it will be good against these types of rushing, impatient, and whatever. So here is how the protocol looks like. You execute a secret key agreement. The secret state is the key, of course, each one of them. The adversary listens in, decides on X and Y. Given the input, use the key as a pairwise independent hash function, G, and send G of X. Okay, so Alice sends G of X, Bob sends G of Y, and the referee simply decides, given G of X and G of Y, whether they're equal or not, that tells it whether X and Y are equal. Okay, so had it been a truly random key, there is nothing Alice and Bob, nothing the referee could do, and therefore, if the adversary can do anything in this case, we can distinguish it from the key from being truly random. And if you think about it, I mean, given G of X, it tells you nothing about G of Y, so therefore you cannot choose Y after seeing. The very fact that you can choose Y after seeing G of X doesn't help you. And also you have no idea whether you're going to succeed or not. So the fact that you can be patient doesn't help you as well. Okay, so we know that for equality, in this model, by sending C bits, you can get probability of 2 to the minus C plus n, lambda. Now I claim that I can go from such a protocol into a secret key agreement. But we'll do it using we'll need a lot of amplification. We'll do a secret bit agreement. It's going to be a single bit. And it's not going to be a perfect one, but luckily for us, we have amplification procedure for that. So an alpha beta secret key agreement protocol is one where Alice and Bob exchange messages, and in the end they decide on a single bit. Alice outputs B and Bob outputs B prime, with probability at least 1 plus alpha over 2 are equal. B and B prime are equal, so they have agreement. And secrecy, no PPT, which guesses an input the transcript and guesses the agreed bit, given that B equals B prime, can succeed with probability greater than 1 minus beta over 2. Okay. So if they agreed on the bit, the probability that the adversary guesses them, it looks like this. This is a secret bit agreement. And if alpha and beta are negligible, we get a secret key agreement. And we can get, once we have it for 1 bit, we can have it for many bits. And what Hollenstein did, he showed that you can go from alpha beta secret key agreement when once 1 minus alpha over 1 plus alpha is less than beta, you can go to all the way to negligible probability. Okay, and the time is polynomial in lab. So we'll get a pretty bad secret bit agreement, and we'll amplify it using Hollenstein. And so what we can show is that given a simultaneous message model with stateful free talk for equality, whose complexity is C of n, where C is less than log n, which is epsilon secure. The adversary cannot succeed with probability better than 2 to the minus 0.7 C, and it's immune to rushing and patient adversaries. This implies the existence of secret key agreement protocol. Okay, so this is where what we show, and the way the protocol works is the way we turn a protocol for equality into a protocol for we'll start with a protocol for equality and turn it into a protocol for secret bit agreement. The protocol, we have tau A and tau B, the secret states of Alice and Bob following the free talk phase. And on input, as we said, on input X and Y, Alice is going to send MA, which is a function of her secret state and A, and Bob is going to send MB, which is a function of his secret state and Y. And so here is how the protocol looks like. Alice and Bob communicate. They generate a secret state. Alice selects a random bit at random, 0, 1, and sends a pair of the 2 inputs, x0 and x1. And then she evaluates MA, which is what she would have sent in the communication protocol with XB, either X0 or X1, and her secret state. And this is her message in the protocol for, this is what MA, she sends Bob the pair MA and X1, always X1. Bob looks at the protocol, Bob evaluates MB and X1 with his secret state. So Bob doesn't send any message, he just evaluates in a bit. And Bob's output bit is whatever the referee would have said given MA and MB. So click, for instance, if things work nicely and X1 was chosen, B equals 1, in and there are no errors or anything, then they agree on the common, the bit they agree is 1. If Alice chooses B equals 1, Bob doesn't make any mistake. Sorry, the referee plus Bob do not make mistakes. Then B prime would also be equal to 1. And otherwise, we hope that if she chooses 0, then we hope that Bob will figure out, Bob plus the referee will figure out that x1 is not really the input of on which Alice was executed the protocol, executed MA, and decide on a 0. That's the hope. And using that, we can show. So we have this is part of the reason why we get a weak result. We can show that this protocol has these parameters, alpha, which is, remember, one very small alpha. Here we have a pretty large alpha, 1 minus 2 to the minus c over 2, and beta, which is 2 to the minus c over 2. And agreement follows roughly the lines I mentioned before. The agreement is going to be simple. Secrecy, we need to construct an adversary or equality from an adversary breaking the SBA. You can break the secret bit agreement. We want to create from it an adversary breaking the equality. And this is essentially what we do here. And the analysis shows that it works, but we are really using the fact that we need to get almost perfect probability. That ratio, the probability should really be exponential in the number of bits that will be answered. And so this raises a lot of questions. The one I mentioned, of course, is whether CRHs are equivalent. And I mean, we still have a gap between VCRH and CRH.
Protocol is efficiency is 2 to the minus c. You need constant c or missing c.
Here?
Yeah,
it doesn't work. Well, it doesn't work beyond 2 to the minus, beyond the seq, which is log n.
Okay.
And probably you can get up to log. But the way, what we claim, what we guarantee is log.
It's open with the way of
Yeah, you want to go beyond the, you want to go beyond the, right? We want protocols with worse error probability, and you know, just give me, you know, a log n protocol which has probability 1/5. You really need the rushing adversary, and then we didn't mention at all rushing in the preset model. You can think of a rushing adversary in this case as well. Preset randomness model. So let me finish here. I'll just show you the pictures of my students. I did not get to talk about, just so that you didn't hear about their work, but at least you'll see their pictures. Thank you.
Okay, just like so in the secret key, like a lower bound, and like in the protocol, we basically care about like a random x0, x1. So like I'm wondering, does this show like this is like actually like a sufficient distribution, like, for anybody who wants to design like a protocol to look at, or like in the security you actually need to.
Oh, that you're saying that give less power to the adversary.
Yeah.
But I'm wondering, the thing is, I'm not sure how it works with the patient. Your thing, what happens if you work with a patient? Because a patient adversary can influence X and Y, X0 and X1, right? A patient, we said that a patient adversary chooses, sorry, X and Y, X0 and X1 are from the secret agreement protocol. The adversary sees the message, chooses X, sees the message on X, then chooses Y. Or decides, no, I'll go to the next one. So therefore, even though here I mentioned, the way I described the protocol, the way I described the secret key agreement protocol, I described it with a random X0 and X1, you do have the power to reject X0 and X1 by the patients, so to speak. The fact that you're a patient, you can modify them. Okay.
Any other questions? Great.